This video looks at section 5.4, definite integrals. And what's going to be happening here is we're going to integrate like we did in the previous section. But once we get that formula that represents the antiderivative, we're going to wind up having these limits of integration, these numbers that represent x values, and we're going to wind up being able to evaluate that formula from A to B. So what you're going to wind up doing is find the antiderivative. That's what that f is, this f right here that we see. Okay, f of x is really the derivative of f of x of capital F of x would have given you that lowercase f of x. So we undid this lowercase f of x. It was the derivative of something, and we found out where it came from. And then what we do is we use this theorem, and we plug in the upper limit to the formula, and then subtract what we get when we plug in the bottom number. Now what we're really doing, this really is the net area, okay, or signed area. Okay. It's the area of the regions above the x-axis minus the area of the regions below. Okay. Now, when you're just asked to evaluate the definite integral, here's your process. You're going to first find the antiderivative. That's the same as the indefinite integral. So 8 would have come from an 8t. Now, in the previous section, we were writing plus c on that, plus some constant on that. Okay. I'm going to show you on this one. We were doing that. But now what we're going to be doing is taking this and evaluating it by plugging in the upper number. Oops, that should be a 1. Plugging in the upper limit and then subtracting from that what we get when we plug in the bottom limit. Okay. And what's going to happen is those c's are going to cancel out. Okay. So when you do these, you will notice that you typically don't even put the c in the beginning, because you know it's going to wind up getting subtracted out once you apply that formula. Now this 32 that we wound up with, okay, after we evaluated this, represents the area under the curve. That 8 that you see is the function y equals 8. So that means up here at 8, we would have this horizontal line. Now the limits of integration are x values. It's from an x of negative, or t values, I guess I should say. So from -3 to 1. And so what we're really finding when we do that calculation is this area. Notice that's 32 because the height of that rectangle would be 8, and it's 4 units across. So there's why you get that 32. Now, on this one, the entire region was above the x-axis. Okay, so this one turned out to just be 32. All right, let's move on and look at question number 2. So here, the first thing I'm going to do is I'm going to integrate each term. So x to the second would have come from x to the third. So I'm going to put a 2 out in front, so when the 3 comes down, it makes the 6 that I need. All right, now over here, the x would have needed an x to the second. This is a little more strange because it's not compatible with that constant that was out in front. So I'm going to do that business of using a 1/2 to get rid of the 2, but then I want to bring the 3 that was already there along for the ride. I'm not going to put a plus c on this because I know it'll just cancel out. What I'm going to do is clean that up and then evaluate it from 1 to 2. Okay. So this becomes 2x to the third minus 3/2 x squared. And what I need to do is plug in the 2 for x, and then I'm going to subtract from that what happens when I plug the 1 in for x. Okay. A lot of mistakes are made on the evaluating part of this, and it's because of this minus sign. It applies to both of these terms here. So remember that your calculators are scientific calculators. You really could just show me your work by doing what I just showed you there, and then if you wanted to, you could just type that whole thing in. Okay. It's quicker for me just to work it out. So this would be 2. 2 to the third would be 8. The power, raising it to the third power, has to happen first before you multiply by 2. Okay, over here I'm going to get 12, 4 times 3, 12 over 2. So that's going to wind up being 6. Okay. Then here I have minus 2 times 1 to the third. 1 to the third is 1, so I'll have a minus 2. And then remember, this negative applies to this next part, so it'll be plus 3/2. So I have 16 minus 6 minus 2 plus 3/2. So that's going to be 16, take away 8. That's 8 plus 1.5. That's going to be 9.5. Okay. All right, now that one I can't really draw easily, but here your job was simply to get what that turned out to be, and you would report 9/2, 9.5. Okay. All right, let's try question number 3. All right, now this one I'm going to do a little rewriting first before I go in. That x is under the square root, so it's really to the 1/2 power. I like it to look like a power function so that I can undo it using the techniques we talked about. So if it's 1/2 there, then it must have come from 3/2, so that when I subtract 1, I get the 1/2. But now that 3/2 would come down in front, so what I can do is think about putting a 2/3 here, the reciprocal here, so that when the 3/2 comes down, it'll cancel out. But I got to remember there was a constant that needed to be dragged along. And don't forget, this is going to get evaluated. Okay. And so you do that little vertical line, and then you put the limits of integration over there. All right, so now I'm going to clean up the expression a little bit, because doesn't that just turn out to be 2? And x to the 3/2, I like to think about it using radicals when I'm evaluating. So it's really the square root of x that's then cubed. So let's plug in the top limit minus what happens when I plug in the bottom limit. Okay. And so I wind up getting 2 times 2 to the third minus 2 times 1 to the third. So that's 2 times 8, which is 16, minus 2 times 1, which is 2, and my final answer turns out to be 14. So that 14 represents the signed area or net area between that original function, so between this function and the x-axis. I can kind of draw that one to give you a sense of it, because the square root of x starts at the origin and then just kind of goes to the right. So, okay, just to give you a sense, it's going to do something like that, right? And so we wound up wanting to evaluate that from an x of 1 all the way to an x of 4. So what that 14 represents is this area under the curve. All right, so you can see, you can kind of think about whether that's reasonable or not. This is 3. And then when you plug in a 4 into that formula, this would have been the height of this right here. Plugging a 4 in would have been square root of 4 is 2. This would have been 6. Okay. All right, let me do that in green. This would have been 6. So if I think about that rectangle, it would have been 6 times 3, or 18 units. But you see how I'd be missing this part right here? So that's why it turned out to just be a little less than that. It turned out to be 14. All right, so we couldn't figure it out directly because we don't have any geometry formulas that will match that picture, which is exactly the reason why this integration idea is so handy, because it allows us to handle dealing with areas of things where there isn't a formula that we could use from geometry. All right, now this one, I can draw that pretty easily. That's this. Okay. X of 8, x of negative 8. This y coordinate would be 2 here and here. My graph isn't the best. So watch what happens on this one. As we're trying to integrate it, I have to think about what the exponent would have needed to be. So after I do the derivative, it turns out to be x to the 1/3. So if I add 1, that would be 4/3. But that 4/3 would come down in front. So let's put a reciprocal of it out in front so it'll cancel out when we multiply by 4/3. Now there would be a plus c, but because I'm actually evaluating, those c's are going to cancel out anyway, so we normally don't write it. And now we're just going to evaluate it from negative 8 to 8. All right, so you might want to rewrite it as a radical before you do that. Oops, almost put a 4 there. So it's a cube root, okay? And then I'm going to raise it to the 4th power. All right, so 3/4 cube root of a positive 8 raised to the 4th power minus 3/4 the cube root of negative 8 raised to the 4th power. And that turns out to be 3/4 times 2 to the 4th, which is 16, minus 3/4 times negative 2 to the 4th. And you see how this is 12, and a negative 2 in parentheses to the 4th is still a positive 16, so this part is also 12, and the net area would turn out to be 0. All right, now, sometimes you're asked to find the area of a shaded region, and here, the area of the shaded region and the value we got when we evaluated the definite integral turned out to be the same. Okay? Here as well, whatever the area of that is, this turned out to just give it to us. But here, both of these shaded regions have an area of 12. This has an area of 12. This has an area of 12, that shaded region. But what the integral does, when the integral sign is on it, it's giving the net area. So these regions that are below the x-axis, you wind up having to subtract. And that's why we wound up having 0 at the end. So this is the answer to the integral question. But if they asked us for the area of the shaded region, if they gave us that picture and they wanted the area of the shaded region, it would equal 24. Okay? So the integral isn't simply the area, it's the net area between your curve and the x-axis, where it's counting the things below the x-axis to be negative and the things above positive. All right, now having said that, that's not going to impact you at all in Cal 1. Okay. All right, let's go ahead and look at this one. This is one involving a trig function. All right, so let me ponder this. So I'm going to look at where the 2 came from, and that came from 2x. And then I recognize cosecant squared of x. that had to do with the derivative of cotangent. I remember it because I know the derivative of tangent is secant squared, so the derivative of cotangent is negative cosecant squared. So I'm going to need a plus here because the negative that I need to have show up is going to come from the derivative of cotangent. Okay, so that right there is the correct formula for the antiderivative. Now we normally put a plus c, but again, we're evaluating. And because we're evaluating this, we don't need the plus c because it'll just get subtracted off. So we're going to evaluate this from the pi over 4 to the pi over 2. Okay, so you're going to do this by plugging in the top number first. Order matters. You need the top number first so that the sign turns out to be okay at the end. Okay, so I'm plugging in the pi halves. Oops, it's not cosine, it's cotangent. And then I'm going to subtract that from that, what I get when I plug in pi over 4 for the x's. Okay. And that minus sign right there goes for both of these, so don't mess that up. So to start with, I can see where I get a pi. Now for cotangent, I'm just going to think about cotangent of pi over 2 for a minute. I know it's cosine of pi over 2 over sine of pi over 2. So if I think about the unit circle, I'm up here. That's really bad. Let me try that again. I'm up here, and the coordinates of that point would be 0, 1. So the value of cotangent there would be 0. So that would be plus 0. Then here I have pi over 2. Okay. And then cotangent of pi over 4 is there. And when you're there, both sine and cosine have the same value. They're both square root of 2 over 2. So when you divide them, you're just going to get 1. So cotangent of pi over 4 would be cosine of pi over 4, which is square root of 2 over 2. And sine of pi over 4, which is square root of 2 over 2, it's going to be 1. So this is going to be minus pi over 2, and then remember that negative on that makes it minus 1. All right, so a pi, take away a half pi, is going to be a pi over 2. I'll write it over here. That's going to be pi over 2 minus 1. All right, now just like other times, you might look in the back of the book and not know if you're right because they might have it where maybe they put that together. Maybe they got common denominators and wrote 1 as 2 over 2. And so then they got pi minus 2 over 2. All right, but I would have accepted this. Most people would have. But if you ever see a different answer, you might just maybe evaluate both of them and see if they wind up giving you the same decimal. That'd be a good way of checking. All right, now these problems are the same except for the integral is not set up for you. You have to do that. So this curve is the y equal 1 over x squared, but we're only looking at it from 1 to 2. So when you're trying to set this up, what you're going to need, since you're looking for area under that curve, area of that shaded region, you're going to need to do an integral from 1 to 2 of the original function with respect to x. You're going to want to change that so it looks like a power function so that it'll be easier to integrate. So x to the negative 2 would have come from, add 1 to it, from a negative 1, but the negative would have come down in front, so we need to get rid of it. We'll put a negative there so that it'll cancel out when that exponent comes down in front. Now we need to evaluate that from 1 to 2. Okay? So I'm going to think about how that's really, let me see if I can just, if you don't mind, I'm going to move this over here now. So that's really negative 1 over x that I'm evaluating from 1 to 2. So I'm going to plug in the 2 subtract from that what happens when I plug in the 1. And that, the minus that I just circled, that's the minus from the formula. But then the expression we're dealing with had a negative in it. So you got to really watch those kinds of details. So this will be negative 1/2 plus 1, which would turn out to be a positive 1/2 when we're finished. Now I was expecting a positive number. And if you look at the picture and you think about a rectangle that's 1 by 1, that whole rectangle should be one whole. So it makes sense for that to be around 1/2. Okay? All right, let's try this one on number 7. Same deal. This is the graph of y equals x plus sine x. Our job is going to be to evaluate that, to not evaluate it, but to integrate that. And when you're looking at it, you can see you want to go from a 0 to a pi. Okay. So you're going to do the integration piece. So you know the x came from an x to the second, but you'd have to have a 1/2 out in front. And sine can be tricky. When you're doing that one, you know sine and cosine come from each other. So just start by saying, okay, I know it's a cosine. But when you check it, the derivative of cosine would have been negative, and there's not a negative here. So you better put a negative so that when you do the derivative of cosine and get negative sine, when you multiply by the negative, it'll give you what you really want. Okay? So that's actually the antiderivative of the function. We just need to evaluate it from 0 to pi. We're going to plug in the pi first. Okay, so I'm going to plug in a pi for x in both of those, and then subtract what happens when I plug in a 0. You don't always get a 0 when you plug in a 0, so be careful. So here we get a 1/2 of pi squared. Okay, cosine of pi, that's over here, would be a -1. Okay. So this one has a formula with a minus in it, and then you've got this minus that's part of the f of b minus f of a part. Okay, then this will be minus, that is 0, but then the cosine of 0, that's over here, is 1. Okay. All right, I'm going to keep going underneath that picture. So I have a 1/2 pi squared plus 1 minus -1. So that's 1/2 pi squared plus 1 plus another 1, that will be plus 2. Now again, they might not have the answer written that way. They might do something like, oh, let's go ahead and get common denominator. So they might do this and then have the answer be pi squared plus 4 over 2. Okay, this would be widely accepted as an answer, but that's what you might see in the back of the book. So if you're ever wondering, you could just plug in and find out what the decimal is for those. Okay, and then you'd know. All right, let's go ahead, even though the video is getting long, let's do one more. This one is a little different in that they didn't draw the picture. So I'm going to help you try to see how to figure out what's going on. So if I factor out an x, there's an x squared plus 1 left on that. Okay, so if I'm thinking about this, that original function being 0, it's only going to hit the x-axis right here. So we're trying to get the area of the region bounded by the graph of y equals x to the third plus x, which I don't have that drawn quite yet. If I'm not supposed to use a calculator, then you know, I'm not sure yet what that's going to be. X equal 2, I know, that's a vertical line over here. And y equals 0 is the x-axis. Okay? So we know this thing only crosses the x-axis at 0 because that's the only way to make the original function equal to 0. So what I thought I would do is just plug in a 2, just so I could begin getting a picture of what this looks like. So like if I plug in a 0, I get 0. And if I plug in a 2, I wind up getting 2 to the third plus 2, that's 8 plus 2, that's 10. Right? So it's up somewhere at 10. And then I know it can't cross the x-axis anywhere else. All I was trying to really check is whether it stayed above the x-axis or not. I might plug in a 1. That's 1 plus 1. That's 2. You don't actually need a graph, but I thought I would share with you how you might be able to construct at least a little bit of it. All I really was checking was that it didn't go below the x-axis. Okay? So I want the area of that region I just shaded. So I'm going to set up the integral. I'm going to do the integral of x to the third plus x with respect to x. And then you see how an x of 0 and an x of 2 would be my limits of integration. So don't plug them in until after you do the integration piece. So now I'm going to integrate. That would have had to come from an x to the fourth, but I need a 1/4 in front to make that 4 go away. Okay. X would have come from x squared, but I'm going to need a 1/2 out in front to make the 2 cancel out. And then I'm going to evaluate that from 0 to 2. So I'm going to plug in the 2 for both of those x's, then subtract from that what I get when I plug in a 0. Okay. Well, that is going to be 0 in this instance. So then it's just 16, because you got to do 2 to the fourth first. So that's 16 divided by 4, that's 4. And then 4 divided by 2, that's 2. I wind up on that one getting 6. And I can look at this picture and think about 6, how likely that would be. I know this was 10, and I know this was 2. Well, that would have been 20, so I'm a little surprised. The rectangle would have been a 20, but I guess I'm cutting out more than half of it because this right here is pretty low down before it curves. So that's not completely unreasonable. All right, and that would be the end.